This is Statistics 243 at UC Berkeley for Wednesday, November 5th. Okay, let's go ahead and get started. I thought what I'd talk about today is we could talk through the third method of doing the QR decomposition, which is this Gram-Schmidt orthogonalization. The idea being partly just to see this idea of orthogonalizing vectors and doing projections and to see how it works out that we can then get a QR decomposition from that. And then the main other thing I wanted to talk about in terms of the rest of the unit, I'll have a few scattered comments, but the main thing I wanted to talk about was looking at a singular value decomposition and thinking about what it means from a statistics perspective and what the eigenvectors and the eigenvalues mean in the SVD. So we'll sort of work through not a real numerical example of that, but we'll work through sort of conceptually an example of that. So how many of you how should I phrase this? How many of you have encountered the SVD in any sort of statistical modeling context? So just a couple of you, a few of you? Okay. All right, so I think it'll be useful to sort of walk through that interpretation. Okay, so in terms of Gram-Schmidt, the idea is, as we've been working through with the Householder reflections and the Gibbons rotations, the idea is, okay, we're starting with this full matrix, dense matrix, X that's n by P, and we're basically trying to get to a representation that looks like this, and we're going to do that by injecting zeros into the matrix. And so we've seen cases where we can pre-multiply by a bunch of these orthogonal matrices, and then we'll do the task of injecting the zeros into X and getting us to this upper triangular representation. So another way we could think about this is, what if we start from the perspective of let's try and make sure the columns of X are orthogonal. Let's try and make a new version of X where the columns of X are orthogonal. In addition, it's going to be an orthogonal matrix, so we also want the columns of X to all be of unit length as well. So, so what can we do? Well, we can start with the first vector, x1, and it's pretty clear how we would make sure that that is of unit length. We just take it and divide by the length of the vector, and then we therefore just normalize the vector. So in some sense, if we just go back to like a two-dimensional picture, I'm just starting with some x1 and x2. They're not orthogonal to each other at the moment. I'm going to take x1 and scale it so that it's going to be of unit length, whatever unit length would be in this particular picture. Okay. And then once I've got that x1, so this is now going to be x1 tilde. I now need to basically take x2 and orthogonalize it with respect to x1. So I just want to take the portion of x2 that's orthogonal x1, and I basically want to remove the portion of x2 that's in the direction of x1. So we can do that by basically projecting x2 down onto x1. And since x1 is already now a unit length vector, that's just going to be the inner product of x2 and the new x1. Okay, so this is now going to be some coefficient c1 that if we multiply by x1 will give us the portion of x2 that's in the x1 direction. Okay. So now we've got that x2 is basically, we've got that there's a portion of the variation in x2 that's going to be the portion we projected down. And if I now take the original x2 and subtract that portion the portion in the x1 direction off of x2, then I should just get the piece of x2 that's in the orthogonal direction. So I'm just doing a projection here. Okay, well now I've got my new x2, which is here. It's not necessarily of length 1 yet, so I need to divide by whatever its length is. So I'm just taking the numerator and putting it in the denominator and getting the norm of it. So I need to then scale that back, but now I've got my new x2 tilde. And if I think about, and then I can just, then I would also, if I now had 3 columns here, I would then take x3, and I would orthogonalize x3 with respect to 1, I'd orthogonalize x4 with respect to x1, and so on and so forth. So now I've got the x1 and x2 are all set, and now I would then move on to x3, and x3 I'd have to orthogonalize with respect to x2. I've already orthogonalized it with respect to x1 in the sort of previous step. So I'm just marching through this iteratively and doing that process of orthogonalization. Questions or comments? So one of the reasons I thought this might be useful is there might be a context in which you have a regression design matrix, and you might want to make sure that you've got orthogonal columns, because that's going to make it easier to do the regression. Because then the regression is basically just going to do the univariate regressions of each of the pieces of each of the x of y on each of the x columns if those are orthogonal. So you could do it in this sort of fashion. It's just orthogonalize the columns with respect, sort of sequentially orthogonalize the columns with respect to each other. Okay, and we can also sort of interpret what the elements in R are as well. If we want to reconstruct the original x, well, this is just going to be, since everything below here is 0, I could just think of Q times R as taking a weighted average of the columns of x. So I'm going to take this element here, and that gets multiplied by the first column of x. So I have a weight on the first column of x. I'll call that R11 times x1 tilde. And then I've got R12 times x1 tilde plus R22 times x2 tilde, and so on and so forth. And so it makes sense. We can represent x1 as just being a coefficient multiplied. We can represent the original x1 as just being a coefficient multiplied by the new x1, and we can represent the original x2 as being a weighted combination of the stuff that's in the new x2 direction and the stuff that's in the new x1 direction. So that's just these two coefficients here multiplied by these new now orthogonal vectors. I think maybe on the next sheet, I guess I might have written out no, I guess I haven't. I didn't actually write out what the elements of the R matrix are, but you can basically work it out by just basically working through what we're doing in terms of the orthogonalization. So I didn't want to say too much more than that. Another way of thinking about this is if I think of my X matrix as my response, as a response matrix with a bunch of sort of Y columns, a bunch of observational columns, I can think about regressing the X considered as observations on Q, and that gives me the R's. So the R's are basically coefficients, so I can think of each column of X as being regressed on Q, and that's going to give me the coefficients in the appropriate column of R. And so if I did that regression, this is sort of a multivariate regression because this X is a matrix instead of a vector Y. So this is just like X transpose X inverse, X transpose Y, except Q is serving the role of X here, and the X matrix is serving the role of the outcomes of the observations here. So you can think of those coefficients as being obtained also via regression if you had the elements of Q in hand. Okay. Any questions about that?
So what was the benefit of using this algorithm compared to previous ones? Is it possible?
So that's a fair question. If we go back to, I wrote a little bit about this earlier on. Yeah, so we had a little bit about this in terms of if I've got an n by px, if I wanted to solve a linear regression problem, a least squares problem, then this is the order of operations for doing it for either Cholesky or the reflections method that we talked about, or for doing Gram-Schmidt. I think if you're not careful, that the Gibbons rotation method is more computationally burdensome than these other methods. So I guess if we look at this, this would suggest that in all cases the Householder method is more efficient than the Gram-Schmidt because it's got 2np squared minus the p cubed. So there might be some trade-offs in terms of numerical accuracy. They're probably not going to be all that important for most purposes. So I guess I did actually have this comment. So yeah, so the Monahan book, which I mentioned in the syllabus, it says that modified Gram-Schmidt is the most numerically stable. So I guess the trade-off here is this is more numerically stable, but it's also more computationally intensive than the Householder method. But as I sort of implied last time, most of the time we're not going to be working with situations where the columns of the X matrix are so collinear that that the numerical accuracy is going to be all that much of an issue. So it's probably in most contexts not going to matter all that much. Other questions? Okay. Let's see what else I wanted to highlight here. There's sort of a cool thing that I found out about last year, which is that if you have a really, really large n, so suppose this X matrix were millions and millions and millions of rows by some relatively small number of covariates, you would think that would be a hard regression problem to solve because you're having to do these tons of computations. And you're having to do this QR decomposition on this huge matrix that you couldn't even fit in memory or even fit, say, on the disk on a single machine. But it turns out that that when you look at this problem, you can actually do a series of smaller QR decompositions where first you do this set of QR decompositions to sub-pieces of X, and then you take the R matrices and you do then sort of another set of QR decompositions to the sub-pieces of R, and eventually at the end of the day, what you end up with is X is equal to this representation. So you can actually get out what the R matrix is, and you can get sort of the pieces of the overall Q matrix in a way that doesn't require you to do the QR on the entire matrix all at once. And sort of an interesting thing to think about here, if you're interested in MapReduce, is you could think about how you would do this in a MapReduce Hadoop Spark kind of context. And you can also do this. There's also a variant on this where you could do it in an online manner, which by online, what people usually mean is you're going to get the data in chunks, and you're going to have to process the value of the data in chunks, and then come up with your final answer in that sort of sequential manner. And so there's a way, if you're getting the X matrix in chunks, you might get X0 first, and then X1, and then X2, and then X3. There's sort of a variant on this algorithm that would allow you to do the QR in that way, and you never actually have to even have the whole matrix on disk on a single machine, say, or even in your possession necessarily at the same time, all at once. Okay, so a quick word about determinants. Basically, anytime we have a decomposition that is a triangular matrix by an orthogonal matrix, which is certainly true for the QR decomposition, then we can think of getting the determinant as the product of the determinants. And what do we know about orthogonal matrices? That they have a determinant that's either plus or minus 1. And what do we know about triangular matrices in terms of getting the determinant of a triangular matrix? It's just the product of the diagonals. So if I have done a QR decomposition, I can get the, and if A were square, if I've done a QR and A, then I can just get the determinant of this by taking the product of the diagonal elements of R, and then I know that the determinant of this is either plus or minus that, because I might not know directly what the determinant of Q is. Or I might not know whether that's positive or negative. Of course, if it's positive definite, that's always going to be plus 1, just by construction. And then just this, basically the same point that we saw in problem set 5, that you would never ever, and if you go ahead and write code that does this, where you take the determinant by doing the product of the elements of a matrix, don't tell anyone that you took this class, because I'm going to be embarrassed that you did it that way. So just like a likelihood, you never take the likelihood as the product of the individual likelihoods for the individual observations. You always do it on the log scale. The same thing, except in very, very small problems, is the case for doing a determinant. You would always want to do the sum of the log of the diagonal elements of the of the triangular matrix instead of trying to take the product of them. Okay. All right, so let's turn to the SVD. So we already saw last time that if you have a cross-product matrix like A transpose A or X transpose X, we can get at the eigendecomposition by doing an SVD, and we've sort of seen that SVDs and eigendecompositions are sort of similar in a way because they're both dealing with these sort of patterns, these vectors that you can think of as features, which are the eigenvectors, and basically variances or weights, which are the eigenvalues. And we've already talked through a full sort of interpretation of an eigendecomposition in terms of taking weighted averages of the columns of the eigenvector matrix. So I guess I already said this last time that the algorithm for coming up with an eigendecomposition is rather more complicated than some of the algorithms that we've already seen for these matrix factorizations. And it involves an iterative procedure where the result basically converges to the factorization that you're looking for. But I thought the useful thing about just pointing this out is that basically the computations that are involved in that iterative algorithm are, at their core, this sort of kernel of the computation is these things like household reflections and Givens rotations, which we've already seen and which you're now familiar with. And that's true both for the eigendecomposition and for the singular value decomposition, which I think I say something about here. Yeah. Okay, but I think maybe the more useful thing to talk about in terms of the SVD is to try and talk through what an interpretation of an SVD would be from a statistical perspective. So I have sort of two examples I wanted to work through. So I'll sort of talk through an example of decomposing a matrix of words within documents, basically counts of words in documents, and thinking about clustering documents and about finding topics in documents. And then I will sort of throw out to you guys a sort of similar problem, which is basically the Netflix problem. So how many of you have heard of the Netflix prize? Okay, a number of you. So I'll talk through that in a second and present that to you. But let's start with the sort of topic modeling example. So this basically comes out of computer science, I think. And so the basic idea is, suppose I have some X matrix that looks like this. So it's going to be a matrix that could be arbitrarily long because n is going to be the number of documents. So this would be document 1 up through document n. And then the columns are the different words in whatever language you're working in. So the columns, let me try and make sure I get my notation. Okay, so suppose I have m unique words in the language, and maybe I throw out some of the really, really uncommon words so that m doesn't get to be immensely big. But maybe m is going to be 10,000 or 20,000 or something like that. In documents, who knows how many documents I have. Okay. So this is basically just going to be a matrix of word counts per document. Okay, so if I have some document, the first document, and the word apple appears 5 times, then I'll have a 5 for whichever of these is apple, and then if this were a document about fruit, maybe there might be a count of the number of times you see the word pear. But if it's a document about computing, then it's also the number of times you see. Then you'd see that the word computer appeared in the document a number of times. So if you do an SVD on this matrix, what you'll get will look something like this. Part of the reason I think it's useful to go through this in an explicit example is whenever I try and go back to try and interpret these sorts of decompositions, to me it always helps to go back to okay, I sort of understand the document word example. Let me try and map whatever my problem is onto the document word example and see if that analogy helps me in understanding what I'm doing. Okay, so I have some now matrix U here, and that's going to be a matrix that's also n documents by k. I'm going to call these topics for reasons that hopefully will become clear once we sort of talk through the problem. This is an orthogonal matrix. This is the U matrix. And I'm going to have a diagonal matrix, a k by k matrix, that are the singular values. And so that's going to be a diagonal matrix. And then I'm going to have another orthogonal matrix, V, which is now going to be k by m. Okay, and so k. So this is now also in sort of in the space of topics, and this is now basically in the space of words. Okay, so one way that a sort of useful way to think about this is if we think about the first document here, which is represented by the first row. These values here are basically weights on the different topics for the first document. Okay, so maybe a document is sort of a mixture of talking about computing and talking about some other topic. Okay, and so if that were the case, then the computing topic and that other, maybe it's a business article, so it's about how Apple's stock was doing. Okay, so it's sort of a combination of a business topic and a computing topic, and so there would presumably be high weights for these two topics for this particular document. Okay. And now if we go over here, the idea is that for any given topic, so let's take the first topic here, there's basically going to be a weight for each of the words, and so if we have a topic that would be a computing topic, then presumably the words that would have high weight would be computer and processor and chip and Apple and things like that, and words like baseball and other things like that would have a low weight on that particular topic. Okay. So we've sort of done this. What the SVD has sort of done for us, if we do this decomposition, is it's basically said documents have different weightings on the different topics. And the topics, what does it mean to be a topic? A topic is just a weighting on the different words that are in the, what's the word I'm looking for? In the language, in the dictionary. And there's another aspect of this is you could sort of think about doing some clustering after you've already done this. Because if we look now at this, if we now look at the U matrix, and we want to basically cluster documents and say this document is like that other document, we could basically find documents where this document and this other document have a relatively small distance between their vector of weights on the different topics between this vector and this vector. And so if you could sort of play games with computing distances between the different documents based on this weighting on the different topics, and you could similarly sort of think about clustering or finding similarities in the different topics by trying to say, this topic and this topic, their vector of weights on the words is at least somewhat similar to each other. So let me pause there. Are there any questions about that? Yeah, go on.
So I feel like the words, the columns, right? If they're all linearly independent, which I feel like, you're talking about like words and documents, they should be linearly independent, right? Otherwise you will kind of make them the same word. If that's the case, then your K becomes pretty much like N, which means like these topics are just words, right? Your M is a lot smaller than N.
Your M is a lot smaller than N. Yeah, so I think maybe one way, probably this is sort of gets at one of the directions that I was going, so that this is a useful point to case to think about this is if you were to, these variances here are the singular values are basically sort of importances of the different topics. So if you basically choose to use fewer topics, smaller number of K here, then you're basically coming up with an approximation of this matrix here with basically a lower rank approximation.
Which is principal component analysis,
right? You could also think about if you're doing principal components analysis, you basically end up with an n by n matrix, but then you sort of throw away the ones that are associated with the smaller eigenvalues. So sort of similar thing here, you could throw away the elements that are associated with the smaller singular values as well. And that would give you a lower rank approximation. So I think that partially answers the question, but let me see here. So so I guess, right, so that's a fair point that if we have n documents and m words, would we ever have a case where k would actually be less than m unless we did this sort of thresholding procedure? Maybe not. Anybody have any thoughts about that? Yeah, Alex.
I don't think k will be less than m is the number of words. I think that's really big. It's your entire dictionary. In k, you pre-specify before you run the model. And you usually choose whether it's going to be like 10 or 1,000 or 3,000.
Yeah, I guess that's sort of what I'm stuck on at the moment, is this question of how do you decide in advance? Not how do I decide that 1,000 is the right value, but if I do decide that 1,000 is the right value, what do I need to do in my algorithm to make sure that I'm getting a 1,000 by 1,000 matrix here instead of, say, a 10,000 by 10,000 matrix if I had 10,000 different unique words?
So I think you have a mapping from words to topics. How do you do that?
Yeah, so I guess part of what I'm not sure about here is whether you can do this in a way where the topics basically emerge from the data without having to sort of choose the topics in advance. So yeah, so I'm not. Okay, so I'm sort of not sure of totally of the answer to your question of sort of how we would sort of implement this if we did want to make sure that we had rather fewer topics than words. But the basic interpretation of what's going on here in terms of topics and words and documents still does hold. And maybe I'll try and look a little bit more after class and see if I can come up with a better answer to that question. Yeah. Other questions or comments? So the other thing I was going to mention here is if we think about reconstructing what are the word counts for a given document. For the moment, let's sort of ignore what the values are here. So let's say for example we just assume these are all ones, so that the weighting of the weighting on the different topics doesn't come into play. Well, what happens here if we want to reconstruct this vector, then that's basically taking this column times this row, and also so that'll give me the first element, and then the second column times this row will give me the second element. So the way that I get the first word, the word count for the first word for the first document, is I basically sum over the topics of the importance of the words in the different topics, multiplied by the importance of the topics for that particular document. So again, I'm taking this sort of weighted average, and if only two of these were not, say, non-negligible, then the only thing that matters is for the count of this first word on this first document is basically sort of the relative importance of these two topics, and then how important the first word is in those two topics. So these could both be close to 0 if that word is not very important for either of those two topics, and presumably that means you're going to have a low count of that word in that document. But in another setting, you might have that if this is the word computer, then this is about Apple stock, then if this is the computer topic, so if this is sort of the computing topic and this is the word computer, then this will have a high weight. It gets multiplied by the fact that this document has a high weight on that topic, and then the result is we get a high count of that word in the document.
So essentially, is this sort of the reverse way of looking at TF-IDF?
I'm not familiar with TF-IDF, so.
Term frequency, inverse document frequency, like when you're doing searches. If like you do a Google search, put in your terms or your words, and the way it sorts it is by looking at documents, and the frequency of the words in those documents is how you'll often get your search results.
Okay, right.
So it seems sort of similar to this, but since it's not something that.
Yeah, I mean, this idea of sort of if you're trying to, you have the words in your search, right? And you're basically thinking about a distance from those words to different documents based on the counts in that in those documents. So it does seem similar in that sort of way of what I was talking about, sort of thinking about clustering based on these weights. And you could imagine if you were designing a system that would basically return a search. Maybe it's a little bit different than this because you're going to have a lot of your document of your search. If it were thought of as a document, it's just 4 words or whatever. So there are going to be a lot of zeros in your row here, but potentially you could think about trying to use this methodology to say, well, what's based on those 4 words? Can I come up with the weighting of my search on the different topics? And then that might allow me to go find other topics that have a similar, other documents that are similar in terms of their weighting on topics, for example.
Just based on distance.
Yeah, based on distance. So that would be, I guess, if you could sort of think of it as distance of this vector to all these vectors, or you could think of it as if you can get it into this topic space, you can sort of think of it as distance in the topic space instead of the word space. Yeah. Other questions or comments? Yeah, Eugene.
TF-IDF utilizes words which are too frequent, so things like we, a, and. But in this case, it seems like if I have a search string which is entirely consisting of common things like pronouns and articles, I'm going to return basically huge amounts of topics which they're related to this.
Yeah, I guess in some ways it depends on if you had excluded some of those common words from doing this initially, which would often be the case. Like, I probably wouldn't put the into here because I don't think it's going to be very informative about doing any sort of modeling of documents. Okay. So then the other example I thought I would let you guys think about for a few minutes is the Netflix problem. So basically Netflix, I don't know when this was. Does anybody know when the Netflix prize was?
A long time ago.
Was it a long time ago? Huh?
I think it was 05 to 09 or so.
Okay. So maybe 5 years ago. So Netflix, you go to Netflix and people, rate how much they like different movies that they've seen. And then when you do, so you've done your ratings, other people have done their ratings, and now you go back to the site, and Netflix says, oh, we recommend these particular movies that you watch based on some algorithm where it says that they've developed that says, something about these movies is presumably similar to some of the other movies that you've seen that you've liked, and therefore we're going to recommend these movies to you. And this comes up a lot in sort of online commerce, this idea of a recommender system. So what I thought might be interesting to do is if you think about the idea that we have a number of people, and each of them has seen some number of movies and have given those movies a rating from 1 to 5. So maybe the first person rated whatever the first movie they rated was a 2, and then they gave a rating of 5 to a couple movies and a rating of 1 to a movie, and so on and so forth. If I were trying to take data that looked like this, which were each person has rated a number of movies, and I'm trying to sort of make it into something that looks like an SVD-like problem, where I have a matrix like this n by p matrix, and then I'm trying to do a decomposition that looks like this. Take a few minutes, find a partner or pair up in 2s or 3s, and think about what you'd have to do to sort of get this into this kind of context, what the meaning of the different matrices would be in the movie context as opposed to the Word document context, and what additional difficulties would you encounter relative to this matrix X in terms of words and documents if you were starting with data that looked like this in terms of the movie ratings. So see what you can come up with, and then we'll talk about it a little bit once you do that.
Yeah. I don't think you have so much something else to do. And then I think it's
Yeah, so if you're grouping,
So yeah, let's just talk about that. So
Oh, no, sorry.
Well,
All right, so the other nice thing about having you guys think for a little bit on your own was I think I came up with a better answer to Guang's question, which is let's think about, so Guang was basically posing that wouldn't this decomposition basically just amount to each topic would basically be a unique word? So basically that this matrix, if this matrix, and if K and M were the same, so this were a square matrix, why would this matrix not just be the identity matrix? Okay, so that's sort of a rephrasing, I think, of what your question was. So let's sort of go back to thinking about this singular value matrix, which is that what this is sort of trying to do to sort of anthropomorphize it is we're trying to sort of come up with the first topic that we try and come up with is the one that explains the most variation and has the biggest singular value up here. So unless it were the case that the words assorted into documents in such a way that the way that we could best explain documents is this is the document that has the word computer in it a lot, and this is the document that has the word pair in it a lot, and this is the document that has the word baseball in it a lot. If it were like that, then it might sort out the way you said. But if there's a lot of correlation between particular words across the different documents, like if computer tends to correlate very highly with the word chip and with the word processor, then what should happen is you should be able to get a high weight here by saying, okay, the first topic is going to have a high weight on chip and a high weight on computer and a high weight on processor, and that's going to do a better job of explaining the variation in this than if we basically had an identity matrix where we just sort of put weights on each of the individual words.
So like unless your documents are pretty much random, otherwise your K is pretty much
Right,
guaranteed.
right. So we're relying on that dependent structure of the words of pairs or triplets or however many how many words, correlations between words when we're thinking of the correlation as being calculated across the documents. Yeah. So then I think what you now that I'm sort of thinking this through a little bit more, I think what you can do to sort of implement this is do this thing, like you said, and I'm glad you pointed this out because I wasn't thinking about it this way. This will probably end up being M. The rank would probably end up being M. So there would not be K's here. But then, if we look at the singular values, what we can probably do is see that a lot of them are very small, and we might end up being able to say, oh, I'm just going to take the top 1,000 or the top 200 or the top 8 or whatever it turns out to be, such that I get a relatively small number of topics, but most of the variation explained by those topics. Okay, so any questions about that second response to the question? Okay, so what about the movie problem? So first off, what's the difficulty in taking something that looks what I roughly described in terms of the movie ratings and how you sort of would understand them if you haven't even introduced the problem to you, and getting a matrix like X here? Yeah.
Not everyone watches all the movies, so a lot of like empty cells.
Right. So we've got a ton of empty cells here. Do you know what your name is? Are you Kevin? Okay. Okay. So we have all the people. But now, everybody's probably rated, I might have rated 5 movies. If you're a real movie buff, you might have rated 500 movies, but you probably haven't rated all however many 20,000 movies or however many there are on Netflix, right? So I've got this, this very sparse X matrix here, where I haven't actually rated all the movies. But if I look at this matrix, it's actually kind of interesting because in some sense, my statistical problem is to basically infer the other elements in that matrix, right? What I want to know is, I've rated these movies, but what would my rating be for these movies if I went and watched them and then went ahead and rated them, right? And then if we were to try and sort of, so suppose that we did actually have the complete matrix. We can talk about how we might do that in a second. It's basically a problem that's called matrix completion when you've got a sparse matrix like this and you're trying to fill in the other elements in a way that sort of respects the dependent structure of the observed elements in the matrix. Okay, so in that case, if we think about this, I guess maybe there's not really much of a question here. We have people here. We have something that we're going to call topics, but maybe it would be worth talking about a little more of what we mean by topics here. And then we have the movies. We have the different movie rate. We have the different movies here. So if we were to look at these guys here and think about let's maybe look at this. Let's maybe think about this matrix here. If we were to think about the weights in this matrix here, and think about what it means to have movie topics. What sorts of things do you think might emerge as your sort of human interpretation of the weights in this matrix in terms of what a topic would mean, or how things might cluster? So it might simply be by genre, like horror movies or drama or action movies or something like that.
Actor or actress.
Okay, so we might have sort of genre. We might have particular actors that are shared across movies that then have some impact on which of the movies, which movies I tend to particularly like. What other things might end up in here?
And let's use like zip code or area also.
Yeah, I wonder how that would play in, because that's not really a movie feature. That's more of a person feature, right? Yeah, it's not. I think that's very relevant for this problem, but I'm not quite sure how it plays into this particular representation. Other things that might pop up here?
Number of nominations, say academic awards, or number of awards.
Okay, so there could be other things that are causing you to like a movie. Maybe you're somebody who doesn't particularly care about what genre something in, and you don't really have any favorite actors, but you're the kind of person who really likes movies that that get a lot of awards, either because they are objectively good movies or subjectively good movies, or because you react to the Academy Awards and those are the movies you see, and you're influenced by everybody else saying those are good movies, and therefore you give them high ratings. Right? So we could sort of think about lots of different kinds of features here. And presumably this is an example of sort of what's the word I'm looking for? Multi-category clustering. So it's not like any movie would only belong to one category in this case. Like if these topics were some of the different genres, and then there was a topic that was a Brad Pitt topic, and there was a topic that was an Angelina Jolie topic, and so on and so forth, we could have the movies can have. If it were an action movie with Brad Pitt, then that could have a high weight on both of those topics. So it's not like it belongs to one and only one topic. Or we could have a horror movie that's also sort of a comedy, and so there might be a high weight on both the comedy and the horror features topics. Yeah.
You need how the rating would give the movie. So like this would cluster based on whether you rated the movie or not. Like I'm about to rate the movie at 1, but am I really more likely to give a higher rating to an action movie than to a drama, or vice versa? It seems to not so correlated.
Well, that's the question, I guess, that would emerge out of doing this sort of analysis is whether there might be if there's no dependency. Let's just for the moment continue to imagine this is a dense matrix instead of having to be filling in the entries. There might be no correlation that it might not be the case that somebody tends to like dramas and on average rate dramas more highly. But I don't think it would take a huge amount of me liking dramas more than I like horror to have it be upweighted enough that it's not like I like all dramas, but on average I like dramas more than I like horror, and therefore it might still be the case that I might end up having a topic that sort of based on looking at the weights and sort of interpreting them still looks like a drama topic, even though it's not that I sort of uniformly give high ratings to all the drama movies. But I think that's really sort of whether these are interpretable and how you interpret them. These are just going to be weights. So I'm saying horror and these other things, but the only way you can attach a label to any of these is by looking at the weights and then trying to interpret, this topic has a high weight on these 4 particular movies. Those are action movies, so I'm going to call that the action topic. But it's just a set of weights. There's nothing that says that has to be the label to it. Okay, so maybe just one final word about the fact that this is actually not a dense matrix. So like I said, this is called the matrix completion problem. I don't remember all of the details, but basically there are iterative algorithms that would, if you sort of impute some values as a starting point into this matrix, like maybe you impute values in here that are just basically based on the row and the column means, and you sort of impute some values so you get a dense matrix. Then you do this factorization and come up with these values. I think you would then, if you had k less than m, I think you would then basically try and reconstruct an approximation of this based on doing this multiplication. You'd get a residual matrix, and I think there's sort of an iterative procedure where you'd basically update the missing elements in this matrix. That's sort of vague because I'm actually not remembering the details of exactly how it works. But to solve this matrix completion problem, there definitely is sort of an iterative aspect to this. If you start with some starting value, you do the decomposition, you basically come up with the decomposition, and then you sort of iterate back and forth. But as I said, I'm not totally remembering the details. All right, so let's quit there. That's basically all I wanted to say about Unit 11. I guess I might make a couple comments next time about doing some of this actually on a computer and in R. And then we'll move quickly to starting in on the simulation unit.